Here we are looking at trigonometric and exponential graphs. We need to be able to recognize these graphs and we need to be able to sketch these graphs. We are starting with the graph of y equals sine x. And we're going to use a calculator to find the values for each of these angles. These are all angles measured in degrees. We're going to use a calculator to work out each of these values, and then we're going to use them to construct the graph. So I'm going to fill out this table of values using a calculator. So this is our table of values. This is what we get if you type all of these into a calculator. So sine 0 is 0, sine 30 is 0.5, and so on. So let's plot these on a graph. So we've got 0, 0, 30, 0.5, 60, 0.87, 91, and then 120, 0.87 again, 150, 0.5 again, 180, 0, then 210 is minus 0.5, 240 minus 0.87, 270 minus 1, and then we go back up to 0 at 360. So we can see the shape that's forming, and this shape is going to repeat every 360 degrees. So this shape is going to repeat the exact same shape. So it's going to go back up to 1, to 0, to minus 1, to 0. So we're going to get the exact same shape repeating, and it will repeat over and over again every 360 degrees, or it could repeat backwards. We could go backwards and repeat the same shape. So this is our graph of y equals sine x. So what we need to know is it starts at 0, it goes up to 1. 1's the biggest thing we can get, and minus 1's the smallest thing we can get. And we have the same shapes that repeats every 360 degrees. And we also need to know that it's symmetrical. So we could draw a line of symmetry at 90 degrees. And so these answers here between 0 and 90 are repeated between 90 and 180. So sine 30 is the same as sine 150. So there's a line of symmetry here at 90. So sine 30 is the same as sine 150. Sine 10 is the same as sine 170. So we need to know there's a symmetrical relationship. We need to know it repeats every 360 degrees. And we need to know that it starts at 0, goes up to 1, back through 0, minus 1, and 0 again. I'm going to try and explain why it looks like this. So you may know that sine x, you've seen the sine function before. Sine x is the opposite divided by the hypotenuse in a right angle triangle. So here's a right angle triangle. We've got the opposite side, opposite our angle, and the hypotenuse. So if you imagine that we've got a hypotenuse here, and we shrunk it down, so it became, the angle became really small, the opposite over the hypotenuse, the opposite would become smaller, so the opposite over the hypotenuse would be really small, and it will go all the way down to 0 when we've got a straight line here. So opposite over hypotenuse will go all the way down to 0, and then as it gets bigger and bigger, the opposite will get bigger, and if I kept making the angle bigger and bigger, the opposite over the hypotenuse will get bigger and bigger until it reached 1. So that explains the first 90 degrees. But then imagine you kept going round. So if this hypotenuse is 1 unit long, think of it as 1 centimetre if you like, 1 centimetre long. So we could rotate it around in a circle, and the hypotenuse would always be 1 centimetre long, no matter where we were in the circle. And if the h is 1, because sine x is O over h, and if you divide by 1, you're just left with what you start with. So sine x, if h is 1, is the opposite, and that is the y coordinate. So if I'm here, my opposite is the y coordinate of this point. So anywhere I am, if I rotate this hypotenuse around the circle, the y coordinate of my dot here, my y coordinate, is going to be the value of sine x. So when we're at 0, the angle 0 here, sine x is 0. The y coordinate is 0. And as we increase our angle, as the angle gets bigger and bigger, as it gets closer and closer to 90, we're going to a y coordinate of 1. So we reach 1 when the angle is 90 degrees. But then when we go past 90, the y coordinate starts going down again. So it's symmetrical. It's going symmetrically down, and it gets to 0 when we're at 180 degrees. Then as we keep going around the circle, our y coordinate becomes negative. So between 180 and 270, it's negative, and it reaches -1 when we get to 270. And then if we keep going round towards 360, we go back to a y coordinate of 0. And we can keep going round with this circle over and over again. We could go round all the way to 720 by just going round again, and we're going to get the exact same answers. We could also go backwards. We could go back to negative angles. So negative 30 is going to be the exact same angle as positive 330. So it's just going to repeat again the exact same pattern no matter how many times we go round in the circle. So that's why we get the same pattern, the same shape over and over again. Let's look at the Cos graph now. So the graph of y equals cos x. So again, we're going to use a calculator to complete this table of values. So cos 0 is at 1. Cos 30 is 0.87 to 2 decimal places. Cos 60 is half. Cos 90 is 0. Then we have minus a half, minus 0.87, minus 1, minus 0.87, minus a half, 0, 0.5, 0.87, and 1. So let's look at the graph of cos x. So let's try and plot these onto a graph. So 0, 1, 30, 0.87, 60, 0.5, 90, 0, and then 120 minus 0.5, 150 minus 0.87, 180 minus 1, and again we're getting this symmetrical shape. This time it's symmetrical about 180 degrees, and we'll get the same pattern repeating every 360. So our graph of y equals cos x looks something like this. And again, it goes between 1 and -1. It's symmetrical this time, about 180 degrees. So this time, 30 degrees is the same as 330 degrees. So the line of symmetry is at 180 this time. And again, I'm going to try and explain this. So we know that cos x is the adjacent over the hypotenuse in a right-angled triangle. So the adjacent is the one in between the angle and the right angle, and the hypotenuse is the longest side. So if we had again a hypotenuse of 1 that we rotated, so as we rotate it, we change the angle. So if the hypotenuse is 1, cos x is just equal to the adjacent, and that is the x-coordinate of this point. So the x-coordinate of this point is the adjacent. So as we rotate this hypotenuse around, the x-coordinate at 0 starts at 1, and then the x-coordinate gets smaller and smaller, going to 0 at 90, and then it turns negative in between 90 and 180, reaching -1 at 180, and then it goes back towards 0 as it reaches 270. It's at 0 again, and then it starts increasing again. The x-coordinate is increasing and goes back to 1 when it reaches 360. And again, you could keep rotating around to get more and more answers. Now we're going to look at the graph of tan x of y equals tan x. So again, let's use a calculator to fill out the table of values which we'll use to construct our graph. So I've completed the table of values. Note that I've given these to 2 decimal places, 0.58. Tan 30 is 0.58 to 2 decimal places. Tan 60 is 1.73 to 2 decimal places. And I've got no answer for 90 and no answer for 270. And you can also see we've got the same pattern. So the first 180 degrees is identical to the second 180 degrees. So let's try and draw these onto a graph. 0, 0. So let's have 1 and -1. 30, 0.58. 60, 1.73. And then no answer for 90. And then 120 comes in at -1.73. And then -0.58 through 0, and then the same pattern repeats again. So we need to figure out what's going on at 90 degrees. So we can think of tan x, as the opposite over the adjacent, or tan x is the opposite over the adjacent in a right angle triangle. And if we had a right angle triangle, we'd have the opposite and the adjacent. If we kept the adjacent as 1 unit or 1 centimeter long, and we kept increasing the opposite side, what would happen to the angle? Or you could think of it as if we kept increasing the angle, what would happen to the opposite over the adjacent? So if we kept increasing this angle, so if we put tan 80 degrees, if we had an 80-degree angle, the opposite over the adjacent would be 5.67. So on a graph, 80 degrees, it would be up here. And if we kept increasing the angle, if we went to 85 degrees, the opposite The opposite over the adjacent would be up to 11.4. So if the adjacent's 1, this will be 11.4 units long. And we can keep increasing the size of this angle, and we get bigger and bigger answers out. And what actually happens is it gets closer and closer to, well, it just gets bigger and bigger. So the closer and closer we get to 90, the bigger the answer we get, but we never reach 90. We get something called an asymptote. So we've got this dotted line here at 90, and our graph gets closer and closer to it, but never touches it. So it gets closer and closer, it never touches it. The closer we get to 90, the bigger and bigger the answers we get, but we never reach 90. So you can keep increasing this opposite length forever, getting bigger and bigger answers, and the angle will get closer and closer to 90, but we're never going to reach 90. So what we get is we get this asymptote. So it's getting closer and closer to this line, but never actually reaching it. So the tan graph looks like this, and it repeats every 180 degrees. So we're going to get the same thing at minus 90 and minus 270 degrees. So the exact same pattern repeating over and over again every 180 degrees. So that's what our tan graph looks like, and it's harder to explain using the circle because it's not as simple as being the x coordinate or the y coordinate. Tan is the opposite over the adjacent. So as we rotate our hypotenuse around, our tan x is going to be the opposite over the adjacent, so the y coordinate divided by the x coordinate. So we can say it's positive, tan's positive in the first 90 degrees. We've got a positive over a positive. But then when we have a positive divided by a negative between 90 and 180, tan is negative. Between 180 and 270, tan becomes positive because it's a negative over a negative, which is positive. And then between 270 and 360, we have a negative divided by a positive, which is negative again. So that explains the sign of the tan graph as we go around the circle. So we need to know the tan graph repeats every 180 degrees. So every 180 degrees we get the same shape, and we have this asymptote at 90 that it gets closer and closer to but never reaches. So tan gets bigger and bigger as it reaches 90. It starts at 0, gets bigger and bigger as it reaches 90, but it never reaches 90, and that gives us this shape. Okay, now let's look at an exponential graph. So this is the graph of y equals 2 to the power of x. So when we've got our x in the power, that's an exponential graph. So let's look at the shape we get. So if x is negative 3, 2 to the power of negative 3 is 1 over 2 cubed, which is 1/8. So I'll write 1/8. 2 to the power of negative 2 is 1 over 2 squared, which is 1/4. 2 to the power of negative 1 is 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. So let's look at this on the graph. So at negative 3, we were at 1/8. At negative 2, 1/4. At negative 1, 1/2. Then 0, 1. 1, 2. 2, 4. 3, 8. and if we wanted to draw 4 and 5, we'd be off the page. So let's look at the shape of this. So again, much like the tan graph, it's going to get closer and closer to this 0 line, but it's never going to reach it. So it's going to come up. And then it gets bigger and steeper as it goes up. So it looks something like that, and it's crossing at 0, 1. And all of these exponential graphs will have the same sort of look. So 3 to the power of x is again going to have the same look, crossing at 0, 1, as will 4 to the power of x. 4 to the power of x, exactly the same, is going to cross at 0, 1. So exponential graphs start very close to 0, but they never touch it. They get bigger. They go through 0, 1. 2 to the power of 0 is 1. 3 to the power of 0 is 1. 4 to the power of 0 is 1. So they're going through 0, 1, and then they get steeper and steeper with the positive values of x. And, well, 3 to the power of x will get steeper, quicker, than 2 to the power of x, and 4 to the power of x will get steeper again. Okay, a question for you to try. So sketch the graph of y equals 3 to the power of x. So all we need to do to sketch this graph is we need to know it crosses at 0, 1. So it starts close to the x-axis. It never touches the x-axis. It crosses at 0, 1, and then it starts getting steeper. So all we need to do to sketch an exponential graph is to get the crossing point at 0, 1, and then this shape. Sketch the graph of tan x for 0 to 360. So give this one a go. So the tan graph started at 0, and then it got bigger and bigger as we approach 90. So we say we've got an asymptote at 90 degrees. And this repeats every 180. So we'll have another one at 270 degrees. And then we just need to get the shape right. So it increased from 0, getting closer and closer to 90, but never reaching it. And then back into negatives through 180, 0. And then the graph is repeating every 180 degrees. So this is what tan x looks like between 0 and 360. Sketch the graph of cos x. So pause the video, give it a go, and press play when you're ready for the answer. So the graph of cos x. So cos started at 1. So it started at 1, went through 90, 0, was at 180 minus 1, 270, 0, and back up to 361. So it's just a nice wave shape. And that is our graph of cos x. And finally, sketch the graph of sine x for 0 to 360 degrees. So the biggest thing it can be is 1. The smallest is -1. And the graph of sine x starts at 0, goes up to 91, back down to 180, 0, 270, -1, and 360, 0. So it looks like this.